Here, we're going to learn how to calculate percent composition by mass, and we'll work through these practice problems. What is the percent composition by mass of hydrogen in H2O? To start solving this, let's take a look at the formula that tells us how to calculate percent composition by mass. And just so you know, sometimes percent composition by mass is referred to only as percent by mass. They're the same thing. Okay, so here's our equation, and it's got a big fraction. The fraction's got a top and a bottom. So on the top of the fraction, we have the total molar mass of just the element. In this case, hydrogen is the element, and I'm going to talk more about the top of the fraction in a minute. On the bottom of the fraction, we have the molar mass of the whole compound. In this case, the compound is water, H2O. Okay, we're going to do some division. We're going to divide the top by the bottom, and then we're going to take that and multiply it by 100%. Okay, so to start solving for this, we are going to want to get a number for the top, and we're going to want to get a number for the bottom here. Let's start on the bottom. Okay, let's start by calculating the molar mass of H2O, of water. Now, you may already know how to calculate molar mass. If you need a refresher, I got a video on that. But just real quick, what we're going to do is we're going to look at the chemical formula here for H2O, which tells us that there are 2 hydrogens and 1 oxygen. Okay, so then we will look up hydrogen and oxygen on the periodic table. Okay, this number here, 1.01, tells us the molar mass of hydrogen, and we got 2 of them. So we do 2 times this number, and then we add it to 1, because we have 1 oxygen, 1 times the molar mass of oxygen. We do the addition, and we get 18.02, the molar mass of H2O, which is how much 1 mole of H2O would weigh. Okay, so that's the bottom here of the fraction. Now let's talk about the top here. Okay, what do I mean when I say the total molar mass of just the element? Okay, well, when we calculated the molar mass of H2O, we added together the molar masses of hydrogen and of oxygen. We combined both of these. But I want to find out the total molar mass of just the hydrogen, not both of these things added together. All right? So if we look at the equation here, if we look at the formula here, we see that we have 2 hydrogens, okay? Each one weighs this much, so we do 2 times 1.01 to get the total molar mass of just the hydrogen. Okay? This is the total molar mass of the hydrogen on its own, and this is the total molar mass of everything, the hydrogen added to the oxygen. So now we can take these values and plug them into the equation. Okay, so on the top, the total molar mass of just the hydrogen is going to be 2.02. And then on the bottom, the molar mass of the whole compound, of the hydrogen and oxygen added together, of the water, is going to be 18.02 times 100%. I'll do this in 2 steps. Okay, so the first step, just doing this division here, is going to give me 0.112 times 100%. I'm rounding this to 3 significant figures because of this number up here. And now when I take this and multiply by 100%, it will move the decimal 2 spots to the right, so I'll get 11.2, and we'll also turn this into a percentage. So 11.2% is the percent composition by mass of hydrogen in H2O. Let's do a couple more. Calculate the percent by mass of iron in FeCl3. We're going to want to get a number for both of these, okay? The total molar mass of just the iron, as well as the molar mass of the whole compound, FeCl3. Let's start out by determining the molar mass of FeCl3. We look at the chemical formula. It tells us that we have 1 iron and 3 chlorines. So we can take a look at the periodic table, do 1 times the molar mass of iron, because we got 1 of them, 3 times the molar mass of chlorine, because we got 3 of those, and get this number for the total molar mass of the whole thing, FeCl3. Okay, now for the total molar mass of just the iron, we'll want to zoom in on iron. Here's its molar mass. We look at the chemical formula, and we only have 1 iron. Okay, so the total molar mass of just the iron is going to be the same as just 1 iron. It's going to be 55.85. Now we got the mass of just the iron, and we got the molar mass of everything together. Let's put it in the equation. We'll take the mass of just the iron, 55.85, and divide it by the molar mass of the whole compound, 162.2, times 100%. I'll do this in 2 steps again. The first step gives me 0.3443, rounded to 4 significant figures, times 100%. And then multiplying this here, we'll move the decimal place over 2 spots to the right, so I'll get 34.43%, the percent by mass of iron in FeCl3. Determine the percent by mass of carbon in C6H10O4. 2 things we want to keep in mind: the total molar mass of just the carbon, and then the molar mass of the whole compound. We'll start with the molar mass of the whole compound, which contains 6 carbons, 10 hydrogens, and 4 oxygens. So we will add their molar masses together, 6 carbons, 10 hydrogens, and 4 oxygens, and get 146.2, the molar mass of all of them added together. Now when we zoom in on just the carbon, we see that we've got 6 carbons here. So we'll do 6 times 12.01, which is how much 1 carbon weighs, and we get 72.06, the molar mass of just the carbon. Now we'll plug these into the formula. We get 72.06 on the top for the molar mass of just the carbon, divided by the molar mass of the whole thing, 146.2 times 100%. The first step is going to give me 0.4929 times 100%. And the second step, moving this over 2 spots and turning it into a percentage, is going to give me 49.29%, percent by mass of carbon in this big compound. So that is how to calculate percent composition by mass, also known as percent by mass. I want to talk about 2 super common mistakes with percent composition so that you won't make them. Here's an example of the first mistake. I'm solving for the percent composition by mass of sodium in N2S2O3, and I'm intentionally making a mistake here. So here's my formula for percent composition by mass. I want to get a number for the top of the fraction and a bottom of the fraction. Here's my calculation for the molar mass of the compound, where I'm adding up the molar masses of the different elements that make it up. And then up here, I have a molar mass of sodium. I put this on the bottom of the fraction, I put this on the top of the fraction, I divide, and I multiply by 100%. Can you spot the mistake here? Well, it's not down here with the molar mass. I'm doing these calculations completely correctly. The problem is up here, specifically with this number. Okay, this number, 22.99, it is the molar mass of sodium, but it's not the total molar mass of sodium in this compound. Okay, this number here is the molar mass of one sodium, but as you can see from the chemical formula here, there are two sodiums in this compound. Okay, so to get the total molar mass of the sodium, we have to take this number and multiply it by 2. Okay, so this is the correct way to do the calculation, taking into account the two sodiums that are in the formula and multiplying this number by 2. This is not the right way to do it, where you just take the number from sodium right off the periodic table. Okay, you have to account for the total molar mass of sodium. And that also means that this number here, 22.99, should be replaced by 45.98. Okay, now the second common mistake has to do with this calculation right here. Here's the math you'll do as part of the final step of the problem. When you divide this by this, you get this. Now, the mistake that a lot of people make is they leave this as their final answer, but this is not the final answer because you still have to multiply by 100%. Multiplying this number by 100% is going to do two things. First, it's going to move the decimal place over 2 spots to the right, so we're going to get 29.08. And just as importantly, it's going to turn this number into a percentage. So we're going to put that percentage sign after it. This is what the final answer should look like. This multiplied by 100%. So those are the two most common mistakes with percent composition by mass problems, and now you won't make either one of them.